This is the first module of chapter 7. The chapter 7 is devoted to find differentiation and integration using numerical methods. In first module, we shall discuss three methods to find derivative of a function. These methods are very simple compared to analytic method, because in analytic method lot of formulas are to be remembered. For example, the derivative of cos x is minus sin x, derivative of sin x is cos x, derivative of log x is 1 by x, and so on. These are not required in numerical formulas. So, in numerical differentiation only one method is sufficient to find the derivative of any arbitrary functions, provided the function is differentiable for any particular point. In this module, we consider three methods to find the derivative of a function. First one is Lagrange interpolation based formula, and other two are Newton's forward and backward interpolation formula. First we consider Lagrange interpolation formula to derive the Lagrange differentiation formula. Suppose the following table of values of y equal to fx are given. That means the values of x and y are given at the arguments x0, x1, x2 up to xn. If the function is given is in explicit form, then from that function we can consider or construct this table of values. Note that the arguments x0, x1, x2 up to xn are not necessarily equispaced. The Lagrange interpolation formula for this given table of values is given by equation 1, which is nothing but phi x equal to wx into summation I equal to 0 to n yi by x minus xi into derivative of w at xi, where w is the product of the factors x minus x0, x minus x1 up to x minus xn. Now we differentiate equation 1 to get the first derivative of phi x, or the approximate first derivative of the given function fx, and phi prime x equal to w prime x into summation yi by x minus xi w prime xi minus wx into summation yi by x minus xi square into w prime xi. That means the first derivative of phi is given by equation 2. Again differentiating equation 2 to get the second derivative of phi, or the approximate second derivative of f, and the formula is given by equation 3, where w prime x equal to summation over j equal to 0 to n x minus x0 into x minus x1 up to x minus xj minus 1 into x minus xj plus 1 up to x minus xn. So, these two formula gives the first and second derivative of phi x as well as the approximate first and second derivative of f. Note that the formula 2 and 3 can be used to find the values of phi prime x and phi double prime x for all values of x except at the given arguments x0, x1 up to xn. In this case, the formula can be written as shown in equation 4, that means phi prime at xj, xj is a given argument, which is equal to w prime at xj into summation I equal to 0 to n, where I and j are different, yi by xj minus xi into w prime at xi plus summation I equal to 0 to n, where I and j are different, yj by xj minus xi. So, the equation 4 gives the first derivative of phi at the given arguments xj, where j equal to 0 to n, and w prime xj is given by the expression xj minus x0 into xj minus x1 up to xj minus xj minus 1 into xj minus xj plus 1 up to xj minus xn, and this expression can be written as the product of I equal to 0 to n, I and j are different, of xj minus xi. Thus, the formula 4 is used to find the first derivative of phi, or the first approximate derivative of fx at the points x equal to x0, x1 up to xn, and the formula 2 is used to find the first derivative of phi or the first approximate derivative of f(x) at any arbitrary point x other than these arguments. The error in interpolation polynomial due to Lagrange is given by this expression Ex equal to Wx. If n plus 1 xi, that means the n plus 1 derivative of f at xi divided by factorial n plus 1, where Wx is given by the expression x minus x0 to x minus xn, product of this factor. This one usual definition of W, and xi lies between the maximum and minimum values of the arguments x0 to xn and x, and the point xi is a function of x, and obviously it is a dependent function on the variable x. Thus, the derivative of E, that means E prime x equal to W prime x, and second factor is unchanged, plus Wx into n plus 2 derivative of f at xi whole divided by factorial n plus 1 into derivative of xi at x. So, this is the expression for the errors occurs in Lagrange differentiation formula, and xi prime x is an unknown function. So, the upper bound of this term cannot be determined. In particular, when x equal to xi, Wxi equal to 0, and in this case the error at any arbitrary point xi is equal to W prime at xi into n plus 1 derivative of xi xi by factorial n plus 1, where xi lies between max and mean values of x0 to xn and x. So, this expression gives the error when x is the given arguments. Now, we consider one example to illustrate the Lagrange differentiation formula for this given table of values. The problem is to find the first derivative of f at 3 and at 1.4. Note that the point 3 is present in the table, but 1.4 is not present in the given table. Here x0 equal to 1, x1 equal to 3, x2 equal to 5 and x3 equal to 6. This is obtained from the given table of values. And for these values, Wx equal to x minus 1 into x minus 3 into x minus 5 into x minus 6. Note that the arguments are not equispaced. And W prime x is given by this expression. Then by the formula, first derivative of f at x1 is approximately equal to first derivative of phi at x1, which is equal to first derivative of W at x1 into summation I equal to 0 to 3 because n is 3, where I not equal to 1, yi by x1 minus xi W prime at xi plus summation I equal to 0 to 3 I not equal to 1, y1 by x1 minus xi. So, using the values of x1, x2, x3, the above expression becomes this expression, that means the first derivative of f at x1 is given by the formula 7. Now, W prime at 1 equal to minus 40, W prime at 3 is 12, W prime at 5 is minus 8 and W prime at 6 is 15. This is obtained from the expression of W prime x. Thus, first derivative of f at 3 is approximately equal to this expression, and after simplification we get 3.43333. That means the first approximate value, first derivative of f at 3 is approximately equal to 3.43333. Now, we calculate the first derivative of f at 1.4. The formula is given by equation 9. Lot of terms are involved in this expression, and for this problem W prime at 1.4 equal to minus 14,62400 and W at 1.4 equal to minus 10.59840. Therefore, the approximate value of first derivative of f at 1.4 is given by this expression. After simplification, it becomes minus 7.00747. So, this is the approximate value of first derivative of f at 1.4. The Lagrange differentiation formula is described. to find the derivative of any function. The function may be given in explicit form or given in a tabular form, but this formula takes lot of computations and the argument of this formula may be equal or unequal spaced. Now we describe two methods based on Newton's forward and backward interpolation formula to find the derivative of any arbitrary functions, but in these formulas the argument must be equal spaced. Now we consider Newton differentiation formula based on Newton forward and backward interpolation formulae. In this case, we assume that the function y equal to fx be known at the n plus 1 equispaced arguments x0, x1 up to xn, where yi equal to f of xi and I equal to 0, 1 up to n. So, for these arguments and for this y, the Newton forward interpolation formula is given by equation 10. This formula is deduced in chapter 2. Now, we differentiate equation 10 thrice to get the first three derivative of the polynomial phi x or the approximate first three derivative of the given function fx. Now, phi prime x equal to 1 by h delta y0 plus 2u minus 1 by factorial 2 delta 2y0 and so on. That means the first derivative of phi at any arbitrary point x is given by equation 11. Now, again we differentiate equation 11 to get the second derivative of phi, that means phi double prime x equal to 1 by h square delta 2 y0 plus 6u minus 6 by factorial 3 into delta 3 y0 and so on. That means the equation 12 gives the second derivative of phi. Similarly, again we differentiate equation 12 to get the third derivative of phi at any arbitrary point x. And similarly, if we differentiate equation 13, then we get the fourth derivative of phi and so on. When x equal to x0, that means when u equal to 0, that means when x equal to 0, then by definition of u should be 0. The above formulae become phi prime x0 equal to 1 by h delta y0 minus 1 by 2 delta 2 y0 plus 1/3 delta 3 y0 and so on. Note that the coefficient of this expression are 1 minus half, 1/3 minus 1 by 4, 1 by 5th and so on. Similarly, the second derivative of phi at x0 equal to 1 by h square delta 2 y0 minus delta 3 y0 and so on. And third derivative of phi at x0 is equal to 1 by h cube delta 3 y0 minus 3 by 2 delta 4 y0 and so on. That means equation 14, 15 and 16 are used to find the first derivative, second derivative and third derivative of phi at the initial point x equal to x0. And the previous definitions are used to find the derivative of phi at any arbitrary point x. The error terms in Newton forward interpolation formula is given by this expression, Ex equal to this expression. Now we differentiate this expression with respect to x, we get the errors in differentiation of Newton forward interpolation formula. So after differentiation, e prime x is given by equation 17 and e prime at x0 equal to minus 1 to the power n, h to the power n and n plus 1 derivative of f at xi by n plus 1. That means equation 17 gives the error at any arbitrary point x and equation 18 gives the error at the point x equal to x0, where xi and xi2 lies between the maximum and minimum value of the arguments x0, x1 up to xn and the point x. So these are the expression for error occurs in Newton differentiation formula. Now we consider one example to illustrate this formula. So a table of values is given. Our problem is to find the value of dy dx, that means the first derivative of y and second derivative of y at x equal to 1 and first derivative of y at x equal to 1.2. Note that here Also x equal to 1 is the point present in the table, but x equal to 1.2, this point is not present in the table. This is the forward difference table which is required to calculate the derivative of different orders. In this case, or the first case, x0 equal to 1, and we have seen that the step length is 0.5. So for this case, u equal to 0, and hence the first derivative at 1 equal to this expression, and after simplification this is equal to 3.36800, correct up to 5 decimal places. And the second derivative at 1 is also given by this expression, or after simplification it is equal to 15.8100, correct up to 4 decimal places. Now for the second case, that means when x equal to 1.2, here also h equal to 0.5, and in this case the value of u equal to x minus x0 by h equal to 1.2 minus 1 by 0.5. After simplification it is equal to 0.4. So for these values of x, u, x0, h, etc., the expression for y prime at 1.2 equal to this expression. After computation or simplification, this expression becomes 6.26948, correct up to 5 decimal places. So this is the first derivative of y at 1.2. Now we consider another formula based on Newton's backward interpolation formula. This formula is similar to the previous formula, that means Newton forward interpolation formula. The Newton backward interpolation formula for n plus 1 argument is given by this expression. Now we differentiate this formula with respect to x to get the first derivative, second derivative and others. Now differentiating the Newton backward interpolation formula, we get equation number 13, and equation 13 gives the first derivative of phi at any arbitrary point x. Now again we differentiate equation 19 to get the second derivative of phi at any arbitrary point x. Third derivative gives this one, this expression, equation number 21. That means equation 19, 20 and 21 gives the first, second and third derivative of phi, and these are the approximate value of the first, second and third derivative of a at any arbitrary point x. In particular, when x equal to xn, then v equal to 0. So in this case, the above formulae reduced to the following form. First derivative of phi at xn equal to 1 by h nabla yn plus half nabla 2 yn and so on. Note that the coefficient in this expression are 1, half, 1/3, 1 by 4, 1 by 5 and so on. And equation 23 gives the second derivative of phi at the point xn. Equation 24 gives the third derivative of phi at the point xn and so on. Now we calculate the errors in the Newton's backward differentiation formula using the same technique applied on Newton's forward differentiation formula. The error occurs in this derivative is given by this equation, where xi and xi2 lies between maximum and minimum values of the arguments x0 to xn and x. And in particular case, when x equal to xn, that means when v equal to 0, the error expression, that means for error at the point x equal to xn is given by equation 25, and which is equal to h to the power n plus 1 derivative of f at xi by n plus 1. Now we consider another kind of differentiation formula called 2-point formula for first derivative. From the relation between finite differences and first order derivative, we know that first order derivative of f at xi is approximately equal to delta yi by h. If h tends to 0, then the derivative is exactly equal to delta yi. But if h is not tends to 0, then the first derivative is approximately equal to the first difference by h. And as by definition of first difference, that means delta yi equal to yi plus 1 minus yi by h, or this is equal to y at x plus I plus h minus y at xi whole divided by h. This formula is known as forward difference formula for first derivative. And in this expression, two values of y are used. So for this reason, this formula is known as 2-point formula. Similarly, from backward difference operator, we obtain as first derivative of f at xi is approximately equal to nabla yi by h. Nabla is the backward difference operator. As by definition, it is equal to yi minus yi minus 1 divided by h, or it is equal to y at xi minus y at xi minus h whole divided by h. This is called the backward difference formula, backward 2-point difference formula. Adding these two formulas, we obtain another formula called the central difference formula for first order derivative, and this one is given by equation 28. That is, first derivative of f at xi is approximately equal to y at x plus h minus y at x minus h divided by twice h. This formula is known as central difference formula, and this formula gives more better result than the formula given in equation 26 and 27. Note that all these formula that means equation 26, 27, 28 gives the first derivative of y at the same point xi. Now we find the 3-point formula for second derivative. From second order finite differences, we know that second derivative of f at xi is approximately equal to delta 2 yi divided by h square, and according to definition of delta 2 yi, this is equal to yi plus 2 minus 2 into yi plus 1 plus yi, and whole things is divided by h square. So it may be noted that the equation 29 gives the second derivative of f at xi, and this derivative includes three values of y, that means yi plus 1 and yi plus 2. Since the three values are required to find the second derivative of f at xi, for this reason the formula is known as 3-point formula. And this is the formula, that means the equation 30 is also a formula to find the second derivative at xi, but this formula is based on the second order backward difference formula. And particularly, second derivative of f at x0 is approximately equal to delta 2 at y minus 1 by h square, which is equal to y1 minus 2y0 plus y minus 1 by h square, which is equal to y x0 plus h minus 2 into y at x0 plus y at x0 minus h whole divided by h square. In general, the second derivative at xi is approximately y at xi plus 1 minus 2 into y at xi plus y at xi minus h whole divided by h square. So these are the formula to find the second derivative of f at xi. So all these formula are used to find the second derivative of f at xi. We know that the first derivative is used to find the maximum and minimum value of a function. That means the derivative is used to find the extremum value of a function. From calculus, we know that if the function is given in explicit form, then first derivative equal to 0 gives the extreme points of the function. But if the function is not given in explicit form, then we can also find the maximum or minimum value of a function from a tabulated values. Let us consider the Newton forward difference interpolation formula to find the extreme values of a function. The Newton forward difference formula is given by equation 32, where u equal to x minus x0 by h. Now we differentiate equation 32 to get the first derivative of f at any arbitrary point x. That means dy dx equal to delta y0 plus 2u minus 1 by 2 into delta 2y0 plus dot dot dot. As per calculus, we know that the maximum or at minimum values dy dx equal to 0. This is the sufficient condition for the extremum. Therefore, from previous equation we have delta y0 plus 2u minus 1 by 2 into delta 2y0 plus 3u square minus 6u plus 2 by 6 into delta 3y0 plus dot 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 equal to 0. That means this is the expression for the first derivative of y. Neglecting the fourth and higher order differences, the above equation reduces to delta y0 plus 2u minus 1 by 2 into delta 2y0 plus 3u square minus 6u plus 2 by 6 into delta 3y0 equal to 0. Let a equal to half of delta 3y0, b equal to delta 2y0 minus delta 3y0, c equal to delta y0 minus half delta 2y0 plus 1 by 3 into delta 3y0. So, using this notation, the above equation reduces to au square plus bu plus c equal to 0. That means it is a quadratic equation of u where a, b, c are given by the above expressions. So, solving this equation, one can determine the values of u at which fx is extremum. So, the above equation au square plus bu plus c equal to 0 gives the values of u. Then the values of x are determined from the relation x equal to x0 plus uh. That means the equation gives the values of u and the expression or relation x equal to x0 plus uh gives the values of x for which the fx is extremum. And the extreme value of fx can be obtained from the equation 32. That means from the any interpolating polynomial. Now we consider an example. Find x for which y is maximum and also find the corresponding value of y from the following table. That means from this discrete table of values, that means from a set of points is given as a tabular form, we have to find the extreme value of the function y for a particular x. So, for this purpose we have constructed the forward difference table. That one is explained in chapter 2. Let x0 equal to 1, we have delta y0 plus 2u minus 1 by 2 into delta 2y0 equal to 0. So, after substituting the values of delta y0 and delta 2y0, we get this equation. After simplification, this becomes u equal to 4.61598. We consider only the linear expression for u, avoiding the quadratic terms. Therefore, the value of x is given by the expression x0 plus uh, which is equal to 1.0 plus 0.5 into the value of u, which is equal to 4.61598. After simplification, this becomes 3.30799. So, this is the value of u corresponding to the value of u, and note that this value is at the end of the given table. So, Newton backward interpolation formula is used to find the value of the function y or the value of the function fx. So, for this reason we calculate the value of v, which is equal to x minus xn by h equal to 3.30799 minus 3 divided by 0.5, and after simplification it becomes 0.61598. This is the value of v. For this x and for the value of v, by Newton's backward interpolation formula, y at the point 3.30799 equal to yn plus v into nabla yn minus 1 plus v into v plus 1 by 2 into nabla 2 yn minus 1. After simplification it becomes 2.04542. So, this is the maximum value of y attained at the point 3.30799. Thus, the approximate maximum value of y when x equal to 3.30799 is 2.04542, correct up to 5 decimal place. 5 decimal places. That means the Newton backward interpolation formula and the Newton forward difference interpolation formula are used to find the derivative of any arbitrary functions, either the function given in a tabular form or given in explicit form. We can find the extreme value of any of the function of the given functions. So, these are the very important result obtained by numerical differentiation. In this module, three differentiation formula, namely Lagrange differentiation formula, Newton forward differentiation formula, Newton backward differentiation formula are derived. Also, the error terms of this differentiation formula are described. Again, we have derived or described 2 points formula, 3 points formula to find the first order derivative and second order derivatives. In the text, we have derived the 4-point formula to find the first derivative of a function at any arbitrary point x. And it is also shown that the maximum or minimum value of a function can be derived with the help of this type of differentiation formula. And all these formulas are explained with the appropriate examples.